What if we could predict a company's sale just by analyzing how much they spent on advertising? And can data actually tell us which advertising channel drives the most sales? Hi everyone, my name is Sibia, and in this video I'll be explaining the major project I completed as a part of my training program with Pregrad. Pregrad is a structured learning platform where I worked on this project to gain practical hands-on experience in real-world development. In today's data-driven world, business don't just rely on intuition, they rely on analytics to make smarter decisions. In this project, I built a multiple linear regression model to analyze how TV, radio, and newspaper advertising affects sales revenue and to identify which channel contributes the most. Now the question is, what is multiple linear regression? Multiple linear regression is a statistical technique used to model the relationship between one dependent variable and two or more independent variables. The general equation is y is equal to b0 plus b1 plus b2 plus b3, where y is equal to sales, b0 is intercept, b1, b2, b3 are coefficients. In our cases, it's TV, radio, newspaper respectively. These coefficients tell us how much sales increases when advertising increases. In this, I used the advertising data set which contains 200 observations, 4 numerical columns, TV, radio, newspaper, and sales. Here, TV, radio, and newspapers are independent variables. Sales is the dependent variable. Sales is called a dependent variable because it depends on advertising spend. All variables are continuous numerical values, and the dataset contains no missing values. For implementation, I used Python along with libraries like Pandas, NumPy, Matplotlib, Seaborn, and scikit-learn. I used Google Colab as my development environment to write and execute the code. Firstly, I imported the advertising CSV in the Google Colab. Then I imported the required Python libraries. Pandas and NumPy for data handling and numerical operations. Matplotlib and Seaborn for visualization. Scikit-learn for building and evaluating the regression model. I imported these because each library serves a specific purpose in the machine learning pipeline. There is no visible output in this step since libraries are just loaded into memory. Next, I loaded the dataset using Pandas into data frame. Head is used to view the first few rows, info to verify data types. As you can see, the output confirmed 200 rows and 4 columns. All variables are numericals and no missing values. I performed this step to ensure that the dataset is clean and ready for modeling. Before building the model, I performed exploratory data analysis. I created scatter plots between TV and sales, radio and sales, newspaper and sales. As you can see from the scatter plot, TV and radio show a strong positive relationship with sales. Newspaper shows weaker correlation. I also generated a correlation heat map further. I performed EDA to understand relationship between variables, check if linear regression is appropriate, identify strong predictors, detect possible multicollinearity. Machine learning should not be applied blindly, so this step ensures correct model selection. Next, I started building the multiple linear regression model. Here, I first imported the linear regression class from scikit-learn's linear model. And then I defined my independent variables by dropping the sales column from the dataset and storing the remaining columns in X. Then I defined the dependent variable y as the sales column. After separating features and target, I created an object called lm1 using linear regression class. Then I trained the model using the fit function. This is the step where the model learns the relationship between advertising spending and sales by calculating the best fitting coefficients. After training the model, I printed the intercept and coefficients. The intercept value is approximately 2.94. This means that if the company spends a zero on TV, radio, and newspaper advertising, the predicted baseline sales would be around 2.94 units. These coefficients are TV 0.0458, radio 0.1885, newspaper minus 0.0010. These coefficients tells us how much sales changes when each advertising channel increases by 1 unit while keeping other variables constant. For every 1 unit increase in TV advertising, sales increases by approximately 0.045 units. For radio, sales increased by approximately 0.188 units, which means radio has a strong impact compared to TV. The newspaper coefficient is slightly negative and very close to zero, which indicates that newspaper advertising does not significantly contribute to sales. This confirms what I observed earlier in the correlation analysis. TV and radio are strong predictors while newspaper has minimal influence. After obtaining the coefficients from the model, I wanted to clearly associate each coefficient with its corresponding features. So I first stored the feature names TV, radio, and newspaper in a list. Next, I extracted the regression coefficients from the trained model using lm1.coefficient underscore. Then I used zip function to combine feature names and coefficients together. Using dict, I created a dictionary that maps each advertising channel to its respective coefficient. This makes the output more readable and easier to interpret. Instead of just displaying the coefficient array, creating a dictionary improves clarity and helps in directly interpreting which feature corresponds to which coefficient. After mapping the feature names with their coefficients, the output is displayed in dictionary format. This clearly shows the impact of each advertising channel on sales. As you can see, for TV advertising, the coefficient is approximately 0.0458. This means that for every 1 unit increase in TV spending, sales increases by about 0.045 units, keeping other variables constant. For radio advertising, the coefficient is approximately 0.1885, which is significantly higher than TV. This indicates that radio has stronger influence on sales. For newspaper, the coefficient is approximately minus 0.0010, which is very close to zero and slightly negative. This suggests that newspaper advertising does not significantly contribute to sales when controlling for TV and radio. Here I generated a correlation heat map using Seaborn. The def.corr function calculates the correlation matrix, which shows the strength and direction of relationship between all numerical variables in the dataset. Then I used sns.heatmap function to visually represent these correlation values. The parameter and not equals to true ensures that the correlation values are displayed inside each cell of the heat map. The heat map displays correlation values ranging from -1 to 1. A value close to 1 indicates a strong positive relationship. A value close to -1 indicates a strong negative relationship. A value close to 0 indicates little or no relationship. As you can see, TV and radio show strong positive correlation with sales, while newspaper has relatively weaker correlation. This helps identify which features are strong predictors before building the regression model. I used correlation analysis to ensure that applying linear regression was appropriate, since linear regression assumes a linear relationship between variables. Then I built another regression model using only TV and radio as independent variables. First, I selected only the TV and radio columns from the dataset and stored them in a new variable called x_TV_radio. Then I initialized a new linear regression model. Next, I train the model using the fit function, where the model learns the relationship between TV, radio, and sales. After training, I use the predict function to generate predicted sales value. Then I calculated the R2 score using R2 score function to evaluate how well the model explains the variations in sales. If the R2 score is approximately 0.8971, it means that about 89.7% of the variation in sales is explained by only TV and radio advertising. This is a very high value, which suggests that these two features alone are strong predictors of sales. When I compared this R2 score with the model that included newspaper, I observed almost no improvement. This indicates that newspaper advertising does not significantly contribute to the predictive power of the model. As you can see, R2 score obtained using only TV and radio is approximately 0.897. This means that nearly 89.7% of the variation in sales is explained by these two advertising channels. This is a very high value, indicating that TV and radio together are strong predictors of sales. Since this R2 score is already very high and adding newspaper earlier did not significantly increase the score, we can conclude that newspaper does not contribute much of model's predictive performance. Here I built another regression model using all three features: TV, radio, and newspaper. First, I selected all three advertising channels and stored them in a new variable called x underscore all underscore features. Then I initialized a new linear regression model. Next, I trained the model using the fit function. After training, I generated predictions using predict function. Finally, I calculated the R2 score to evaluate the performance of this model. If your R2 score is around 0.8972 or very close to the previous value, you can say the R2 score using all three features is approximately 0.897. This is almost the same as the model using only TV and radio. This indicates that adding newspaper does not significantly improve the model's performance. Therefore, TV and radio are most impactful advertising channels for predicting sales, while newspapers contributes very little to the model. The R2 score using all three features is approximately 0.89721, as you can see on the screen. When compared to the model using only TV and radio, which had an R2 score of 0.89719, the improvement is extremely small, almost negligible. This indicates that the newspaper advertising does not significantly improve the predictive performance of the model. Therefore, TV and radio are primary drivers of sales in dataset. By comparing both models, I concluded that a simpler model using only TV and radio is sufficient as it provides nearly the same accuracy with fewer variables. Next, I implemented train test splitting to properly evaluate the model's performance on unseen data. First, I imported train test split to divide the data set into training and testing sets. Then I separated the independent variable and dependent variable. Using train test split function, I divided the data into training and testing with fixed random state to ensure reproducibility. The model was trained using the training data and predictions were generated on the test data. This helps evaluate how well the model generalizes to new unseen data. I calculated RMSE root mean squared error using mean squared error. RMSE measures the average prediction error in the same units as the target variable. Lower RMSE indicates better model performance. I also calculated the R2 score on the test data. This tells how well the model explains the variation in sales for unseen data. Using train test split prevents overfitting and ensures that the data performs well not only on training data but also on new data. After applying train test split, the model achieved an RMSE of approximately 1.40. This means that, on an average, the model's predictions differ from the actual sales value by 1.4 units. The R2 score on the test data is approximately 0.916. That means that about 91.6% of the variation in sales is explained by the model on unseen data. An R2 square of 0.91 on test data means the model generalizes well, it's not overfitting. The relationship between advertising and sales is strongly linear. This makes your model academically solid. Since the test R2 score is high and the RMSE is relatively low, the model demonstrates strong predictive performance and good generalization ability. Here I removed the newspaper feature and built a new model using only TV and radio. I dropped both sales and newspaper from the dataset to keep only relevant predictors. Then I applied train test split to evaluate the model properly on unseen data. The model was trained on the training set and predictions were generated on the test set. Finally, I calculated RMSE and R2 score to evaluate performance. This step was performed to verify whether removing newspaper improves or maintains the model's performance while simplifying the model. After removing the newspaper feature and validating the model again using train test split, the RMSE decreased to approximately 1.39 and the R2 square increased approximately to 0.918. This indicates that the simplified model using only TV and radio not only maintains performance but slightly improves it. Therefore, newspaper advertising does not significantly contribute to predicting sales, and the simpler model with TV and radio is more efficient and interpretable. That concludes that TV and radio are primary drivers of sales in this dataset. Through exploratory data analysis, model comparison, and proper validation, I concluded that multiple linear regression model using only TV and radio provides strong predictive performance with high accuracy and better model efficiency. Then I used the Yellowbrick library to visually evaluate the performance of my optimized regression model. I imported the prediction error visualizer, which helps compare actual versus predicted values. I passed my trained model LM5 to the visualizer and fitted it using the training data. Then I evaluated it on the test data using score method. Finally, I displayed the visualization using show function. This plot compares actual sales value with predicted sales value. If the model performs well, the points will align closely along the diagonal line. The closer the points are to the line, the better the model predictions. Clustering points near the diagonal line confirms that the model predicts sales accurately with minimal error. The plot showed that predicted values closely follow actual sales value, indicating a good model fit. Then I created an interaction feature by multiplying TV and radio advertising budgets. Now, what interaction means? If TV and radio together create a stronger combined impact, then individually the interaction term will improve model performance. This new feature captures the combined effect of TV and radio on sales. I then selected TV, radio, and the interaction term as independent variables, and sales as a dependent variable. I splitted the data set into training and testing sets to properly evaluate the model on unseen data. I trained a new linear regression model including the interaction feature. I generated predictions on the test dataset. I evaluated the model using RMSE and R2 square to compare its performance with previous models. Adding an interaction term helps determine whether the effect of one advertising channel depends on the level of another channel. After introducing the interaction term between TV and radio, the model's performance improved significantly. The RMSE reduced to approximately 0.70 and the R2 square increased to approximately 0.979. This means that nearly 98% of the variation in sales is explained by the model. This indicates that the combined effect of TV and radio plays a crucial role in influencing sales. The improvement suggests that the impact of TV advertising on sales depends on the level of radio advertising and vice versa. Now, what this means conceptually. Earlier, our model assumed sales is equal to B0 plus B1 plus B2, where B1 is TV and B2 is radio. Now it assumes sales is equal to B0 plus B1 plus B2 plus B3. B1 is TV, B2 is radio, and B3 is TV into radio. That extra term captures synergy. And clearly, synergy exists in this dataset. By incorporating feature engineering through an interaction term, the model captured deeper relationships within the data, resulting in significantly improved predictive performance. Here, I used the Yellowbrick library again to visually evaluate the performance of interaction model. I passed the trained interaction model to the prediction error visualizer and fitted it on the training data. Then I evaluated its performance on the test data and displayed a prediction error plot. This plot compares the actual sales value on the x-axis with the predicted sales values on the y-axis. If the model performs well, the points should align closely along the diagonal references. As you can see, the points are tightly clustered around the diagonal line, confirming that the model predictions are highly accurate. The visualization confirms that numerical results showing that the interaction model captures the underlying relationship between advertising channels and sales very effectively. And with this, we've completed our project. This project was not just about building a regression model, but about understanding how data translates into meaningful business insights. From data exploration to model improvement, each step helped me develop analytical thinking and practical machine learning skills. This project was not just about building regression model but about understanding how data translates into meaningful business insights. Through exploratory data analysis, model comparison, feature engineering, and validation, I learned how to evaluate and improve predictive models effectively. The final interaction model demonstrated that the combined effect of TV and radio advertising significantly influences sales performance. Such models can be applied in real world business scenarios to help companies optimize advertising budgets, identify high impact marketing channels, and make data driven decisions to maximize revenue. Overall, this project strengthened my analytical thinking and gave me practical experience in applying machine learning to solve business problems. The structure of this project can be applied to various domains such as real estate price prediction, healthcare risk analysis, financial forecasting, and demand prediction. The same analytical workflow can be adapted wherever data driven decision making is required. I hope this would help in future. Thank you for watching.